Sinusoidal sequences. The sinusoidal sequence can be expressed as x of n equal to a cos omega a cos of omega naught n plus theta. If n is dimensionless, if n is dimensionless, then both sigma omega naught plus theta have units of radians, units of both the unit of radians. Two examples of sinusoidal sequences are shown as before. Figure in 1.3. As before, the sinusoidal sequence in equation 1.58 can be expressed as a cos of omega naught n plus theta equal to a or that is real part of e power j of omega naught n plus theta. Where 1.13 we already have seen this one. Phi of n condition, phi of n equal to cos of pi n by 6, x of n equal to cos n by 2. This one already we have seen. A this one condition. Okay. So in this a cos of omega naught n plus theta, that is a cos this part equal to what? That is real part. That's why real part of e power j of omega naught n plus theta. This theta is coming here, but real part. That's why e power j omega. This omega naught n also coming here. Both are coming here. E power j only. This is real part of e power j only for cos. That is cos is the cos for real part, sin for imaginary part. As we observed in the case of the complex exponential sequence in equation 1.52, the same observations, equations 1.54, 1.56 also hold for sinusoidal sequences. For instance, the sequence in figure 1.13a is periodic with fundamental period 12, but the sequence in figure 1.13 is not periodic. Is not periodic. Okay, we'll see that one afterwards. As you observed in the case complex exponential sequence in equations, the same observations in equations 1.54, 1.56 also hold for sinusoidal sequence. For instance, the sequence in figure 1.3a, 1.13, this one sequence periodic with fundamental period 12, fundamental period 12. But the sequence in figure 1.3 is not periodic. This is the periodic, but the sequence here is not periodic. Sorry. Is with periodic, but the sequence A figure is periodic. So figure A is periodic, but B is not a periodic. This is not a periodic. This is cos of pi 6 pi divided by 6 n. Here x of n equal to cos n by 2. This is not a periodic. Okay. Here, so what is the difference actually? Previous 3, 6, 9. Yeah. This point is there. Different. So here 0 is not coming here. Here coming. That's why period. Okay. This is the difference. Remaining all are same. That's all. Systems and a classification of systems. Systems representation. A system is a mathematical model of a physical process that relates the input or excitation signal to the output or response signal. System is a mathematical model of physical process that relates the input excitation signal to the output response signal. Let x and y be the input and output signals. Let x and y be the x is the input, y be the output signals respectively of a system. Then the system is viewed as a transformation or mapping of x into y transformation. This transformation is represented by mathematical notation, that is y equal to tx. Mapping transformation, the x and y, x is the input signal, y is the output signals in the system. This is the system. That box is the system. Okay. Here excitation is there. Input means excitation. Output, this is the response signal. Let x and y be the input and output signals respectively of a system. Then the system is viewed as a transformation. The system is viewed as a transformation or mapping of x into y. This transformation is represented by mathematical notation y equal to tx. Here t is the operator. T is the operator representing some well-defined rule by which x is transformed into y. Where t is the operator. T is the operator. T is the operator. T is the operator. Okay. Representing some well-defined rule by which x is transformed into y. Transformed into y. This is the operator. Operator and input transformed into y. Relationship 1.60 equation is depicted as shown in figure 1.14. In figure 1.14, system with a single or multiple input and the output signals. A, here the this is y equal to tx, this figure A, single or multiple input. This is the multiple input. Here only one input. T is the operator. T is the operator representing some well-defined rule by which is X is transformed into Y, transformed into Y by this operator T. This is the system. Okay. Relationship 1.60 is depicted shown in figure. Okay, this one shown in figure. A. Multiple input and or output signals possible shown in figure 1.14b. Here, this is the multiple input, multiple input. Okay, this is the x1 to xn, x to x3, and up to xn. And our output signal also multiple. Yeah, y1 to y1, y2, y3, y4, y5, y6, y7 up to ym. Here xn up to output signal is possible shown in figure. We will so here that's why I mentioned multiple input and output signals. This is figure B. Here single input, single output. This is that is y equal to t. Yes, t is the operator in this system. This is the system. That is x is transformation to y, transformed into y, transformed into this is a very important point. Transformed into y. Okay, this is so continuous time and discrete time systems. Same what we have seen in a signal. That same concept here because signal operation going on in this system only. So signal happening, signal transformation or process uh, going on in this system only. Continuous time and discrete time systems. If the input and output signals x and y, x is the input signals, output signal is the y, are continuous time signals, then the system is called a continuous time system. If that input and output signals are continuous time signals, then that system is also say continuous system, continuous time system. In figure A 1.158, continuous time system figure A, discrete time system figure B. So here x of t continuous input, output continuous output, the system. Here t is the operator. So what signal input continuous signal going on, here some operation going on, then output continuous. That's all. X of t, that one is in continuous x direction. Okay, t. So that's why x of t. Here y of t. Okay, how much going on? Okay. If the input and output signals are discrete, same like here continuous, here discrete. Input signals, output signals, discrete time signals, discrete time signals. Then the system is called a discrete time system. Yeah. Time, excessive time, but that is discrete time signals. These are discrete time signals.